Good day, Molweni 2020, Grade 12 Physical Sciences learners. Our second topic is equilibrium constant, Kc. From the previous topic, remember that reversibility of reactions is leading to the concept of equilibrium. Equilibrium occurs until the system is constant. Equilibrium occurs until the system is constant. Then we talk of equilibrium constant, Kc, K capital letter, C subscript. When calculating the equilibrium constant for a reaction, take note of the following rules. Check if the chemical equation is balanced. The chemical equation is balanced by the number of moles. Only gases, in brackets small letter g, and aqueous solutions, in brackets small letter aq, are included in the Kc equation. In the previous lesson, we said the factors that influence the equilibrium are the temperature, pressure, and concentration. Kc means the value of equilibrium is determined by using concentrations of species in moles per decimeter cube. Kc means the value of equilibrium is determined by using concentrations of species in moles per decimeter cube. Kc changes as temperature changes. Pressure is directly proportional to temperature from grade 11 syllabus. In science, it is important to understand the chemical equation and the formula. Start by understanding the chemical equation written in letters of alphabet. Let me read the chemical equation in the textbook. A moles of reactant A reacts with B moles of reactant B, double arrows, showing reversible reaction, to form as C moles of product C plus D moles of product D. Formula is as follows. Kc, the equilibrium constant, is equal to the concentration in square brackets of C raised to the number of moles C multiplied by concentration of D in square brackets raised to the number of moles D. These are the products. Divide by concentration of A in square brackets raised to the number of moles A multiplied by concentration of B in square brackets raised to the power B. Concentration is indicated by square brackets. Concentration is indicated by square brackets. So in this textbook, they are on top of page 211. Equilibrium constant Kc is the product of the concentrations of products raised to the number of moles per product divided by the product of concentrations of reactants raised to the number of moles per reactant. In summary, I would say that Kc is equal to concentration of products raised to the number of moles per product over concentration of reactants raised to the number of moles of reactants per reactant. Referring to the previous example of blue copper sulfate, CuSO4 5H2O, reversible reaction sign, arrows showing both sides, opposite sides. 1 mole of copper sulfate, CuSO4.5H2O, forming a 1 mole of copper sulfate, CuSO4, plus 5 moles of water, 5H2O. Then the equilibrium constant Kc. Kc would be copper sulfate, CuSO4, in square brackets, multiplied by concentration of water in square brackets raised to the power 5 over the concentration of CuSO4.5H2O in square brackets. Kc for the experiment we started in lesson 1 would be concentration of copper sulfate, CuSO4, multiplied by concentration of water. So they are both in square brackets, but the concentration of water is raised to the number of moles, 5, over the concentration of blue copper sulfate, CuSO4.5H2O, in square brackets. Also look at the Haber process reaction equation. Example on page 211 in Study and Master textbook. 3 moles of hydrogen gas reacts with 1 mole of nitrogen gas in order to form a 2 moles of ammonia 2NH3 reversible reaction. Then Kc would be concentration of ammonia NH3 raised to the power 2 over concentration of hydrogen gas raised to the power 3 multiplied by concentration of nitrogen gas in square brackets. Remember that the concentrations of solids in small letter s and pure liquids in small letter l remain constant in value. Remember that the concentrations of solids in small letter s and pure liquids in small letter l remain constant in value, will have the value of 1. Therefore, solids and pure liquids are excluded from the Kc equation. Therefore, solids and pure liquids are excluded from the equilibrium constant equation. For example, calcium carbonate, CaCO3 in solid form. Once you heat it, it's going to form a calcium oxide in solid form plus carbon dioxide. Calcium carbonate in solid form burns in order to have a calcium oxide plus carbon dioxide. Calcium carbonate is dissociating into calcium oxide in solid form and carbon dioxide in gaseous form. Write the Kc for the chemical reaction. Then apply the above rule. Kc is equal to concentration in square brackets of carbon dioxide. Kc is equal to concentration of carbon dioxide in square brackets. Example 1. Hydrogen gas and iodine gas are mixed in a closed vessel and kept at a temperature of 425 degrees Celsius. After reaching equilibrium, the reaction mixture was analyzed and found to be concentration of hydrogen gas, H2 in square brackets, is equal to 1,14 moles per decimeter cube, comma. Concentration of iodine gas in square brackets, I2, is equal to 2,61 moles per decimeter cube. Then concentration of hydrogen iodide, HI in square brackets is equal to 8,41 moles per decimeter cube. Calculate the value of the equilibrium constant at this temperature. The balanced equation is on page 213, test yourself number 2. The balanced equation is on page 213, test yourself number 2. Hydrogen gas, 1 mole of hydrogen gas reacts with 1 mole of iodine gas in order to form 2 moles of hydrogen iodide in gaseous form. This is a reversible reaction. Write the formula of the equilibrium constant for this particular reaction. Kc equals to concentration of hydrogen iodide Hi in square brackets raised to the power 2 over concentration of hydrogen gas H2 in square brackets multiplied by concentration of iodine gas I2 in square brackets. When substituting the values, put them in common brackets instead of square brackets. When substituting the values, put them in brackets instead of square brackets. Equals to, in brackets, 8,41, close the brackets, raised to the power 2, over concentration of hydrogen gas, in brackets 1,14, close the brackets, multiply by, in brackets 2,6, close the brackets. Then the answer is 23,77. You can check the answer. Then the value of Kc has no units. The value of Kc has no units. The units have cancelled each other. The units have cancelled each other. Kc is 23,77. Kc is greater than 1. If Kc is greater than 1, it indicates that the equilibrium will shift to the right. The forward reaction is more favored. More products will be formed. More hydrogen iodide products will be formed. Then the second example. The following equilibrium exists in a container. 2 moles of carbon monoxide in gaseous form plus 1 mole of oxygen gas in gaseous form forms 2 moles of carbon dioxide in gaseous form. At equilibrium, the concentration of carbon monoxide in square brackets CO equals to 1,2 moles dot per decimeter cube. The concentration of oxygen gas in square brackets equal to 1,8 moles per decimeter cube, comma, the concentration of carbon dioxide gas in square brackets equal to 1,6 moles per decimeter cube. Then you write the formula for the equilibrium constant for this particular reaction. Kc equals to, in square brackets, carbon dioxide, you close the square brackets, raised to the power 2, raised to the number of moles, over concentration of carbon monoxide in square brackets, multiplied by concentration of oxygen gas in square brackets, which is equal to, then I said, at least if you are substituting the values, you don't put square brackets, you put ordinary brackets, equals to, in brackets, 1,6, close the brackets, raised to the power 2, over, in brackets, 1,2, close the brackets, raised to the number of moles 2, multiply by, in brackets, 1,8, then you close the brackets, which is equal to 0.99. And you can see even in this problem, there are no units because units are cancelling each other. In this particular problem, Kc is smaller than 1. If Kc is smaller than 1, it indicates that the equilibrium will shift to the left. The reverse reaction is favored. More reactants will be formed. So more of carbon monoxide reacting with oxygen will be formed. Enough for the day.